So this video is about section 4.9, applications to Markov chains. We're going to look at one kind of application of matrices, and it involves some probability, but just the very basics of probability theory. There's one kind of problem that this is all going to come down to, so we'll work through that problem together when we get to it. And the topic of this section is related to that population example that we considered back at the end of chapter 1. I think it was 1.10. So let's get started here. And the handout is posted in Canvas, so you have access to the notes. So first of all, a probability vector is defined to be a column vector that has no negative entries and the entries add up to 1. So here are a couple examples. Notice the entries as you come down add up to 1.0. And as you can probably guess, we think of those entries as being probabilities of certain events. A stochastic matrix is a square matrix with columns that are probability vectors. So here is a stochastic matrix, where just notice as you go down each column, the entries add up to 1. You can have 0 as an entry, but you can never have a negative entry in a probability vector or a stochastic matrix. A Markov chain is a sequence of probability vectors that will denote x0, x1, x2, so on and so forth, along with a stochastic matrix P, such that x1 is equal to p times x0, x2 is equal to p times x1, x3 equals p times x2. In other words, x sub k plus 1 is always equal to p times x sub k for all k. The vectors x0, x1, x2 in the sequence are called state vectors. In a sense, they represent successive states of a certain system. So here's the example we're going to look at. If Mr. P has eggs for breakfast on day k, then there's a 20% probability that he will have eggs for breakfast on day k plus 1. There's also an 80% probability of no eggs on day k plus 1. If Mr. P does not have eggs for breakfast on day k, then there is a 60% probability that he will have eggs for breakfast on day k plus 1, a 40% probability of no eggs on day k plus 1. So we consider this given information that sets up our problem. Where these probabilities came from, who did the statistical analysis, we don't know. We're just assuming this is given information. And we're going to consider two different situations. I call them A and B here. A is the situation if Mr. P has eggs on day k equals 0. And B will be consider the situation if we don't know exactly what Mr. P has for breakfast on day k equals 0, but we just know there's a 70% probability that Mr. P has eggs on day k equals 0. Now, we need a little bit of notation to set this up, and you're not going to have to go on your own go through all this setup. So I hope it's not too overwhelming, but I just wanted to motivate a little bit that in the end we're going to have this very simple matrix, stochastic matrix, that we're going to work with. So just to help us think about things here, I'm calling P sub k the probability that Mr. P has eggs on day k. And P sub k prime is the probability that Mr. P does not have eggs on day k. So notice that these two probabilities, P sub k and P sub k prime, have to add up to 1, right? If one of them is 0.2, the other's 0.8. If one is 0.1, the other's 0.9. So these are just complementary kind of probabilities. There's no connection to derivative, by the way, that the prime just means another probability. That's the only significance of that. So now let's think about what p sub k plus 1 is the probability that Mr. P has eggs on day k plus 1. We can think of that probability in the following way. We can think of it as the probability of, well, we're going to break it down by whether he had eggs the day before or not. Either he had eggs on day k and he has eggs on day k plus 1, or he had no eggs on day k and he has eggs on day k plus 1. So this considers, it really breaks down the situation of having eggs on day k plus 1 into two, what we would call separate events, or non-overlapping events of either having eggs on day k and the other having no eggs on day k. Now, I worded this in terms of using the words or and because we can use some basic principles of probability. When you have or, you can add the probabilities as long as they're non-overlapping events, and these are non-overlapping. And the word and basically can be translated into a product or multiplication of probabilities. You don't have to know this theory. I just want you to believe that this seems like a reasonable way to go. So if I break this down now, I can say this probability p sub k plus 1 will be the probability of eggs on day k, that's p sub k, and the probability of eggs on day k plus 1. Now that is, there's a 20% probability that he will have eggs on day k plus 1 if he had eggs for breakfast on day k. And we are assuming eggs on day k, so we can multiply by the 0.2 for eggs on day k plus 1. Now, or plus, if he has no eggs on day k, that's p sub k prime, and there we're going to multiply by the probability of having eggs on day k plus 1. Well, this is a different probability now, because if he had no eggs on day k, in our statement of the problem, if he had no eggs for breakfast on day k, there's only a 60% probability of eggs on day k plus 1. And that's where the 0.6 comes from here. And so the sum of these two products is the probability of eggs on k plus 1. Now we can also write down the probability of not having eggs on day k plus 1. And we can break it down in this same way, where we separate it into two situations, whether he had eggs on day k or no eggs on day k. So he either had eggs on day k and he had no eggs on day k plus 1, or no eggs on day k and no eggs on day k plus 1. So this is only the situation where he has no eggs on day k plus 1. And eggs on day k that's p sub k probability. No eggs on day k plus 1. Well, given that he had eggs on day k, we know this probability is 0.8 from our statement of the problem. Or plus no eggs on day k, so p sub k prime, times no eggs on day k plus 1. Well, in this case, the probability is going to be 0.4 because that's given the fact that he had no eggs on day k. Okay, so we get this expression. Now, what we're going to call x sub k is a probability vector, pk and pk prime. And x sub k plus 1 will be p sub k plus 1 over p prime k plus 1. So x sub k plus 1 can be written, now I'm going to use these expressions from up above. P sub k plus 1 is this stuff. P sub k plus 1 prime is this stuff. I fill it in. And the idea here is this looks like, well, it is a scalar times a column vector plus another scalar times a column vector, which we're very familiar with from our course, that we can think of that as 2 by 2 matrix times a column vector. So x sub k plus 1 is this matrix of probabilities that just happens to be a stochastic matrix times this column vector, but this column vector is x sub k. So this situation of eggs for breakfast is a Markov chain with stochastic matrix with these entries, 0.2, 0.8, 0.6, 0.4. And you can kind of just sum it up by saying the columns kind of correspond to whether you have eggs or no eggs on day k. The rows correspond to whether you'll have eggs or no eggs on day k plus 1, at least the probability of those things. So now, really, the setup, it's just sort of plug in to do some of this analysis. If eggs on day k equals 0, so this is the first time we're actually looking at that situation A in the statement of the problem, where we're being asked, consider the situation if we know Mr. P has eggs on day k equals 0. That means the x sub 0 probability vector is 1, 0. In other words, P sub 0 is 1, P sub 0 prime is 0. We absolutely know he has eggs on day 0. And then to find the probability that he has eggs on day 1, the next day, we take our stochastic matrix times x0, just multiply that out. And it shouldn't be surprising that it turns out that the probability as eggs on day 1 is 0.2, and no eggs on day 1 is 0.8, because we know he had eggs on day 0. But now we can continue. X sub 2 is a stochastic matrix times x sub 1, and we end up with these probabilities. Now, 0.52, 0.48, so slightly more chance that he'll have eggs. X3, we multiply again. We get another, we get the x3 probability vector. It turns out on day 3, there's a smaller chance that he'll have eggs than no eggs. And then I just went ahead and calculated x4, x5, x6. And I just, if you look at these decimals that I'm getting, it looks kind of like maybe we're approaching some sort of limiting value. And that's really the interesting conclusion we're going to see when we're through with this whole section. Okay, so that's the part A analysis. And you know, there's no one answer here. We could just go on and on and on and on. But it does sort of look like these probabilities are stabilizing in a certain way. That the probability he has eggs is about 43%. The probability he doesn't have eggs is 56%. Oh, I guess sorry, I forgot I had a couple more, 7 and 8 for that A situation here also. Okay. All right, now let's go ahead and look at the B situation. So B has a different starting situation. In situation B, we're assuming the probability he has eggs on day 0 is 0.7, no eggs is 0.3. So our x0 vector starts out as 0.7, 0.3. Again, we multiply by the same stochastic matrix to get x1, and then again to get x2, again to get x3, x4, x5. So while the initial probabilities are a little bit different, it does kind of look like, to me, we're heading toward the same limiting values. Compare x sub 6 for situation B to x sub 8 for situation A. They look very similar. So it seems that no matter what the initial state, that is, no matter what probability vector is chosen for x0, x sub k approaches a limit as k approaches infinity. In our example, the limiting value for both situations A and B seems to be about 0.43 and 0.57. Well, it turns out that a probability vector Q, well, this is just a definition right now, a probability vector Q is called a steady state or equilibrium vector for a stochastic matrix P if PQ equals Q. So if when we multiply by the stochastic matrix, we actually just get the vector Q back again. We get the same vector at the next stage. So what I'd like to do now is let's take our stochastic matrix from the Mr. P breakfast example, and we're going to see if we can find a steady state vector for P. And this is what I want you guys to be able to do. So what we have to try to do is solve PQ equals Q for the vector Q. And we can go ahead and just call those entries Q1 and Q2. And remember, we want Q to be a probability vector. That's something we're going to have to think about as we go through this solution. So now, PQ equals Q is the same thing as PQ minus Q equals the zero vector. I can write that as PQ minus Q times the identity matrix equals 0. And that allows me to factor out Q. I can write this as P minus I times Q equals 0. And so what we want to do is we want to solve this homogeneous equation. Something we've done over and over again, so we're going to make use of a concept that we're very familiar with here in our course. And so I need P minus I. P minus I is 0.2, 0.8, 0.6, 0.4 minus 1, 0, 0, 1. So we're taking the difference of two matrices. 0.2 minus 1 is going to be negative 0.8. Then I get 0.6, 0.8 here. 0.4 minus 1 is negative 0.6. And I want to solve this homogeneous system, so my augmented matrix is just 0, 0 on the end, right? And I want to row reduce. And it's really nice to start out by just adding row 1 to row 2, because we have opposite entries here, right? We're just right off the bat going to get 0, 0, 0 in that second row. And then if I want to get a 1 in that lead position, so I'm going to divide by row 1 by negative 0.8, and I'm going to get negative 3/4, I believe, so 0.6 over negative 0.8. And I got my reduced form here, so I can say Q1 minus 3/4 Q2 is 0, because I was saying my variables were Q1 and Q2. Q2 is free, so the matrix Q is going to be of the form 3/4 Q2 Q2, or Q2 times 3/4 1, where Q2 is any real number. Okay. Now that's a general solution for the homogeneous equation, but there's an added twist to this problem. Q must be a probability vector. And so that means Q1 plus Q2 have to add up to 1. And so what I'm going to do is just take this form and see, this is going to give me one particular solution. That's a probability vector. So while there are infinitely many solutions to the homogeneous equation, when I take 3/4 Q2 plus Q2 and say that's got to be equal to 1, I get, let's see, 1 plus 3/4 is 7/4 Q2 is equal to 1. I think I get Q2 is equal to 4/7. And Q1 is equal to 3/4 times Q2, which is 3/4 times 4/7 is going to be 3/7. And so my vector Q, there's only one probability vector that satisfies these conditions, and it's going to be 3/7, 4/7, and let's see, I'll pull out my calculator here just for the record. I think you might be able to guess what the decimal for these might look like. 3 divided by 7 is, this is about 0.4286. 4286, and 4 divided by 7 is about 0.5714. And so that's the steady state vector for the Mr. P eggs for breakfast problem. So what it means is no matter what it seems like this is giving, this 0.4286.5714, when we look back at what we were approaching for both our A situation and our B situation, it looks like both of those were approaching this steady state vector, and that's absolutely true. And in fact, so this is the kind of problem you need to be able to do, where you won't have to set up the stochastic matrix, but you'll have to be able to take a stochastic matrix and find the corresponding steady state vector. So just to wrap things up here, a stochastic matrix is said to be regular if for some power p, p to the k has all positive entries. And here's an example of a regular matrix. In fact, that's the matrix, stochastic matrix from our problem. Once a power has all positive entries, all future powers will have positive entries. Here's an example of a stochastic matrix that's not regular, because p to the k equals 1001 for all k. Here's one, I don't know where I got this example from. This P is a stochastic matrix. I used a Desmos matrix calculator, give me P squared, because it's kind of a mess of decimals. And again, as soon as I see that I have a power that does not have 0 entries, we call P regular. Now you're not going to have to apply this theory. I just want you to see this theorem. So because it turns out that if P is a regular n by n stochastic matrix, then P has a unique steady state vector Q. Also, for any initial state x0, if xk plus 1 equals P sub xk, then xk approaches the steady state vector Q as K approaches infinity. So in our breakfast example, we did have a regular stochastic matrix, and so that steady state vector is unique, which means given any initial x0 vector, any initial probability vector, the situation will always approach the steady state vector Q no matter what. If the stochastic matrix was not regular, it turns out the steady state vector might not be unique, and we're not going to see any situations like that. For us, the steady state vector will always be unique. So what I outlined in red here is what you need to know. If you're given a stochastic matrix, you need to be able to find a steady state vector for that stochastic matrix.